The past decades, and in particular the past few years, have seen more and more aspects of our lives move online. This includes healthcare, banking, education, and remote work, among many others. This comes with great benefits. It makes doing our business, both personal and work-related, much more convenient, and it has enabled people to engage with others independent of location and mobility. But it also comes with risks to privacy, risks that our online accounts, communication, and identities might be compromised. To make this work, people need to know that they can trust these new systems. If we were to continue the way things currently are, it would require users to put more and more trust in the platforms that provide these services, trusting that their privacy will be protected, and that their accounts will be safe from compromise, and that their communication will remain secure. At the same time, there's a societal movement to shift the responsibility of trust to the user, so that the user only needs to trust themselves and their device. For example, there's a push to support end-to-end encryption in the communication platforms that provide messaging and calls, so that data is encrypted from the recipient before it leaves the user's device. Another place where we can see this kind of shift is in the web ecosystem. There's currently a movement to get away from third-party cookies to protect people from unwanted tracking when they use the internet. However, much of the legitimate functionality requires cross-site information, which is built using this kind of cookies. Many of the proposals for addressing this center around storing information in the browser, putting the user's device in the center of data collection, rather than an external database. Finally, transparency initiatives like certificate transparency allow users to monitor a service for correct operation. In certificate transparency, the aim is to ensure that all public websites are included in a public log, where they can be audited for correctness. Each user's browser will be able to efficiently verify that this log is behaving correctly. So we have these three directions: making the user device the center of data collection, putting the user device in charge of protecting the data, and allowing the user device to monitor the service provider for correct operation, all setting the user at the center of making the services trustworthy. This approach, that at making the user and the device they're using at the center of trust, is a very natural fit for our digital identities. Of course, there are additional challenges in this space. Any solution needs to be flexible. We know users' privacy and security goals vary from one setting to another, and ideally an identity solution would be flexible enough to allow for this. It also needs to be scalable. To be practical, any solution will need to scale to support hundreds of millions of users. Finally, and perhaps most importantly, these solutions need to be usable. We want solutions that work for real users, not security experts. In this session, Microsoft researchers Christian Paquin, Greg Zawaruka, and Esha Ghosh talk about three identity projects that center trust on the user. Christian discusses efforts to make the user's device the central repository for identity data and to allow for flexible and privacy-preserving use of this data. Greg looks at a problem in the secure communication space, where the service needs to authenticate users in a way that is private but very lightweight. Finally, Esha looks at the problem of key distribution in end-to-end encryption and how a user's device can monitor a service provider to ensure that it is correctly distributing encryption keys on his behalf. These projects touch on the three directions mentioned previously: making the user device the center of data collection, putting the user's device in charge of protecting the data, and allowing the user's device to monitor the service provider for correct operation, all putting the user at the center of making the services trustworthy. I'll now turn it over to Christian.
All right, thank you, Melissa. Everyone is familiar with this iconic New Yorker cartoon that states that no one knows you're a dog on the internet. And this is true in part because there is no built-in identity layer for the internet. It's been a long-standing goal of the identity community to fill the gap and to build such a layer, to allow users to present attributes about themselves seamlessly to various service providers, as easily as it is to pulling your cards out of your wallet in real life. However, we're now stuck with a set of identity silos where users have to manage a multitude of passwords, credentials, and devices for their different spheres of activities, without an easy way for them to use them seamlessly in an interoperable manner. When made aware of this goal, cryptographers were quick to provide a solution. We can do that using so-called minimal disclosure technologies, a set of user-centric, privacy-protecting cryptographic systems that allow the issuance and presentations of identity claims in an unlinkable manner over the full privacy spectrum. You might have heard of the term anonymous credentials for these systems. But since anonymity is only one end of the identity spectrum, the other being full identification, and most scenarios requiring some sort of in-the-middle pseudonymity, we prefer the generalized term of minimal disclosure. Here's an example to illustrate the capabilities of such credentials. Say an issuer wants to issue a credential to a user encoding their certified name, date of birth, and address. The credential is cryptographically signed by the issuer, preventing forgery and modifications. The credential is linked to a private key under the user's control, preventing theft and replay attacks by malicious parties. So far, this sounds like conventional PKI certificates, but we'll soon see the difference. The user can choose to present a credential to a verifier using their private key, creating a proof, for example, that their name does not appear on a denial list without disclosing their actual name, and proving that they are over 21 without actually disclosing their date of birth. The verifier doesn't need to see the address in this case, so it would simply not be revealed. You might be surprised by this ability and by the fact that the user does not need to disclose all the encoded information to preserve the authenticity of the credential, meaning the issuer's signature, as it would be the case with conventional cryptographic signatures. But these powerful disclosure techniques use zero-knowledge proofs to achieve these counterintuitive measures. The user can later choose to present the same credential to a different verifier, disclosing a different set of claims. For example, here, the full name and the address. The date of birth would not be needed in this case, so it would simply not be revealed. The user randomizes each presented credential, making sure that the cryptographic wrapping contains no data that could be used to correlate the issuance and presentation of the credential, or used to correlate two presentations of the same credential, which would prevent unwanted user tracking. So let me repeat this. Other than the attribute values presented by the user, which could be identifiable, of course, the users of the credentials are unlinkable, even if the issuer and the verifiers collude. These type of systems have been built and implemented, prototyped, and piloted before. For example, CardSpace was a Windows 7 wallet implementation for the identity meta system, an open framework allowing users to store identity cards in their desktop and with the ability to present them to various websites online. At MSR, we developed the uProve minimal disclosure technology, supporting all the features I described previously, providing open specifications and open source code. You can go to microsoft.com/uprove if you're curious. We integrated uProve into CardSpace and we piloted the technology in various projects, most notably in the Attribute-Based Credentials for Trust, or ABC for Trust in short, a EU-funded research project. We gained a lot of experience and demonstrated the powerful capabilities of these technologies, but failed to achieve adoption in the real world and integration in the Web 2.0 protocols. There are many reasons for that. For example, usability was an issue because it's great to offer all these powerful disclosure capabilities to users, but it's difficult to describe them in UI. Example, like what data is disclosed to whom, especially compared with the competing federation protocols that silently and transparently redirected users across websites during authentication. Of course, this was bad for privacy because it gave a lot of visibility to the service providers, but users didn't really care at the time. There was an extra complexity as well to analyze and implement these features due to the advanced cryptography needed to realize them. We also suffered a performance hit because the new cryptography wasn't as efficient as the conventional and optimized one. Last but not least, privacy was not a big selling point. Web 2.0 was, after all, built on a business model that monetized tracking users' data and activities. So the privacy protections were not welcomed with open arms by the service providers. But things are changing, and users are demanding today more control and more privacy in the systems they use, particularly when it pertains to their identity. So we are now in a renaissance for identity technologies and protocol. This is due in part due to a strong privacy push across the industry, brought by new regulations such as the GDPR and new capabilities in the operating systems and in browsers, such as Do Not Track and the privacy modes. We also see a desire for unlinkability with the decline of third-party cookies and the consent dialogues popping up all over the websites. Users are also getting used to present stronger identities and entitlements thanks to new capabilities in their devices. For example, the FIDO Alliance passkey specification allows users to authenticate to website using strong cryptography without the need of passwords. Privacy Pass is another example of a protocol allowing users to present anonymous tokens to service providers, proving they are entitled users without the need to answer CAPTCHA challenges, while preventing tracking. The COVID pandemic affected everybody, and it also saw the emergence of new types of credentials. As an example, we participated in the development of the Smart Health Card framework deployed in the US, Canada, and many other countries, allowing millions of users to present immunization proofs and lab test results in the form of a QR code they control to various verifiers, allowing people to get back to some normalcy in their life. Given these trends in identity, we now see a renewed demand for advanced cryptography to provide minimal disclosure and privacy in various protocols and settings. As an example, ISO recently released the Mobile Driver's License Standard, specifying how to issue electronic documents to user devices, such as mobile phones, and providing the ability to disclose only a subset of the encoded attributes when presenting a credential either online or in person. Another example relates to JSON Web Tokens, which is a popular format to send attribute information on the internet, as it is used in OpenID and the OAuth protocols. The OAuth working group is working on a new draft called Selective Disclosure JSON Web Tokens, which would allow the issuance of long-lived tokens from which a selective subset of the attributes could be disclosed on demand by the user, opening up the scenarios where these type of tokens could be used. Finally, Claim QR is a project we recently released that generalizes the Smart Health Card framework, allowing issuers to encode not only medical information, but claims of any type, giving the users the ability to modify the issued QR code to only present the required information for a particular transaction. You can visit the Microsoft GitHub page under the Claim QR project to learn more about this. So as we've seen, there's been a lot of progress in updating the protocols, and there's also been a lot of progress in academia to make the early generations of crypto schemes more secure, more efficient, and more usable. We have new schemes such as BBS Plus, a multi-show signature that will help us build improve minimal disclosure credentials. We have tools like ZK Snarks, which will allow us to create more efficient zero-knowledge proofs, bringing these technologies closer to adoption. My colleague Greg will go into more details later in the talk about some of these things. The research groups around the world and the open source community are hard at work prototyping and building many of these building blocks, creating new identity protocols to encapsulate them, such as the W3C verifiable credentials and JSON Web Proof protocols. Many of these have matured enough and to be used in broader identity scenarios. And it's now a perfect time to revisit the vision of building a user-centric identity system with strong security and privacy for the internet in its current state, but also its extensions in the Web3 and the future metaverse. So this is where our road ahead lies. So I will pass it on to Greg. It will take you to the next section. Thank you.
Okay, thanks, Christian. So I'll talk a little bit about some of the options at the cryptography layer to realize minimal disclosure credentials. And then I'll talk about using these credentials in the Signal end-to-end encrypted messaging application. So far, we've been discussing minimal disclosure credentials as a general primitive for user identity. If we zoom in, though, the space is actually quite rich, and there's a range of cryptographic mechanisms that we can use to provide different levels of identity. At one end, we have systems like uProve, EDMX, and BBS+. These have the most features, and they'll work in the largest number of scenarios. As Christian noted, they're fully portable and can be used for what we think of as a traditional identity. And as we move across the spectrum, we have schemes that are more specialized to certain scenarios, and they're interesting because this means they can be further optimized. In the middle are something called keyed verification credentials. They were invented here at MSR. And these are restricted to the case when a single party both issues and verifies the credentials. So think of a closed system like a transit card. So the transit authority both issues the transit passes, perhaps on phones or smart cards, and also verifies them when users present them to get on the train. The authority can ensure that a user has a valid pass for the current area without learning anything more. It's a more limited form of identity restricted to a single system or domain. And if we take this specialization to the limit, we end up with anonymous tokens. These are also in the setting of a single issuer and verifier, but they go further and strip out all the information. So instead of encoding a list of attributes about the user, only the fact that the user has a valid token is communicated to the verifier. This is a very basic type of identity. It's useful for recognizing users that have previously been authorized to access a resource. What's important, though, is that the token adds unlinkability between the authorization and access steps. And there are some things that, in between these categories that I've left out, but these are the main ones. And while standardization and deployment at the fully featured end of the spectrum has been kind of slow, we're seeing much more recent activity with the more specialized types of credentials. And I'll give an example in the context of Signal in a few slides. So the interesting thing about the features versus cost trade-off is the shape of the curve. So it turns out that by giving up very little in the way of features, we get a much lower cost in terms of CPU, time, or size. And this was our motivation when we came up with the keyed verification credential notion, that there are many scenarios that need fewer features, so it would be worthwhile to design something more specialized. Traditional anonymous credentials are built using special digital signature schemes, and these have the most features and flexibility, but they also have performance drawbacks and tend to require that we make stronger assumptions when analyzing security. Implementations can also end up being more complex as well. In the keyed verification setting, since the issuer and verifier are the same party, we can construct these with something called a cryptographic MAC, which stands for Message Authentication Code, as opposed to a digital signature. This is nice because MACs are simpler, they're easier to design and analyze, and they're generally more efficient. And finally, in the anonymous token case, the underlying crypto primitive is something called an OPRF, which stands for Oblivious Pseudorandom Function. And despite the complicated name, is actually a little simpler than the MACs we use for the KV credentials. The main advantage of tokens is that they're especially efficient when the user presents them, since they just have to send the token. Only the verifier has to do some computational work to verify it. But for the previous two credential types, presenting the credential usually requires a zero-knowledge proof from the user. So now I'll tell you about a specific use of key verification credentials in the Signal private group system. Okay, first let me explain what Signal is for those that aren't familiar with it. So it's an instant messaging app that replaces SMS on your phone and can also be used on your PC. And it's, it's known for having end-to-end encryption and strong privacy. End-to-end encryption means that the Signal service acts as a delivery service for encrypted messages, and it never sees the user's messages in the clear. Users have a public-private key pair, which they generate on their device, and they're in full control of. They first exchange public keys with their contacts, and then encrypt, all communication. Exchanging public keys in an authenticated manner is a classic problem in key management, and later in this talk, Esha will describe a new approach that's well suited for user-centric systems like Signal. So there's the Signal app and the Signal protocol. And the protocol is used in other instant messaging apps as well, like WhatsApp and Facebook and Skype. And this technology is developed and operated by the Signal Foundation, which is a nonprofit. They do everything open source. And part of their goal is to match the functionality of other IAM apps without compromising user privacy. So end-to-end encryption is great for one-to-one chats, but how do we secure group chats? Well, securing the actual messages can be done with the secure channels that are in place for one-on-one chats. But we also have to manage the list of users that belong to a group so that users know who to send the group messages to. And keep in mind that we want to do this privately. So like simply storing the list on the service provider in a database, like other apps might do, isn't really an option. Users could try and maintain the state amongst themselves somehow, but it's hard to synchronize the list as it's dynamic and users are coming on and offline all the time. So this is the problem we set out to solve. Melissa Chase and I from MSR, along with Trevor Perrin from Signal. Okay, well, let's take a look at how this could be done without any privacy, just as a starting point. So as I said, the service can just store the group identifiers along with the list of users that belong to the group and maybe some other metadata. And then when someone new joins the group, they just contact the server and the server sends them the full state of the group. This has some obvious drawbacks since the service could modify groups without being detected, or they might be compelled to share the information about who's in a particular group. But still, the system is reliable and it's easy to extend with new features and kind of build on it. So some version of this would be ideal. Our solution will maintain this list on the server approach, but we're going to encrypt all of the data using a key shared by the group members. So the encryption immediately addresses the privacy issue since now the service can't read any of the data. But at the same time, the service can no longer authenticate users in order to enforce who's allowed to download the encrypted list or to make modifications to a group. We also want the service to be able to validate the data so that users aren't creating groups full of junk or non-existent members. And of course, this is all non-trivial when the service doesn't have access to the data. So let's focus on the authentication question. So we need users of a group to be able to authenticate against an encrypted entry in the list. So they should be able to kind of come up to the server, point to one of the ciphertexts in the database, and convince the server that the user ID that's encrypted there is their user ID. Right? So using our keyed verification credentials and a companion encryption scheme, user Alice can prove the following. So I have an authentication credential issued by the Signal service that's valid for use today, and the user ID in the credential matches the user ID in the ciphertext C for the group G. So notice it's enough to reveal only that the user ID and the credential and ciphertext are the same. You don't have to reveal the ID itself. And then the server has assurance that Alice is a group member. This is done with a zero knowledge proof, and so no additional information is revealed beyond this statement that we're proving. Also note that a similar proof can be used to prove that ciphertexts don't encrypt junk. When a user is adding themselves to a group, they can prove that the new ciphertext encrypts a certified user ID, again, without revealing it. And all this is done quite efficiently. It's roughly the cost of establishing a TLS connection, and the storage overhead on the server is about 80 bytes per group member. So if you're a Signal user, you've probably already been using this for a while, along with millions of others. It was put into production sometime in 2020, and it's completely transparent to the user experience. You wouldn't even notice that it's happening. Since then, it's been the basis for more group-related features in Signal, like encrypted group calls, group links, as well as a permission system to manage groups. If you're interested in the details, and I had to leave out lots of details, you can find our paper, the Signal blog, or you can have a look at the source code. And one final thought, I just want to point out that this is an interesting proof point. So it demonstrates that non-trivial services can be implemented securely and reliably without access to user data. It goes well beyond the basic functionality of just delivering encrypted messages and was done by a moderately resourced project. So let's start thinking about what other services can be made private in a similar way. And with that, I'll turn it over to Esha, who will talk about the authenticated key distribution problem that I mentioned earlier. Thank you.
Thank you, Greg. Greg has already mentioned the problem of authenticated public key exchange for encrypted communication systems. In this talk, I will dive deeper into this problem and discuss the recent developments in key transparency in this space. So just a quick recap. In encrypted communication systems, the contents of the communication can be decrypted only on the devices of the participating users and not in transit. Greg gave an in-depth example for the Signal app, but in the recent years, we have seen several other encrypted communication apps for chats and meetings, such as Signal, WhatsApp, iMessage, Zoom, Teams, and etc. So the first step of building a encrypted channel of communication between two end devices is for them to exchange their recent public keys corresponding to the secret key that's on their devices. So for the purpose of this talk, the solid keys are the secret keys and the transparent ones are the corresponding public keys. But how do the users get their latest public keys? This is a hard problem. And the end-to-end encrypted systems solve this by letting the service provider maintain a directory of the public keys of its users and distribute it on their behalf. Now, this also opens up, while this is great for usability, this also opens up the avenue for person in the middle or PIM attack. Why is that? It's because as a compromised service provider, or SP, or one that's coerced to act maliciously, they can generate some private key and public key pairs and then distribute fake keys on behalf of the users. So in this toy example, you see it generated the red and purple key pair. And then when Bob asks for Alice's public key, it gives this red fake key. And for Alice, it pretends that the purple key is Bob's public key. So by doing this, it has essentially created a PIM channel between them so that it can listen on in the traffic and re-encrypt it back to Alice and Bob's devices. Obviously, this is very bad. This breaks the fundamental promise of an end-to-end encrypted system. So most chat apps these days provide a mechanism of QR code scanning to detect if such an attack is happening. And the QR code scanning lets the devices scan each other's QR code to ensure that they're seeing the correct public keys of the other devices. But to actually have this in practice, the devices need to point to each other, which means they have to be next to each other physically, which is often impractical, and beyond that also it is well understood the users don't do this very often, and this is not a user-friendly solution. If we switch to end-to-end encrypted group meetings or calls, the expectation of encryption is similar there, which is that nobody else except Alice, Bob, and Charlie in our toy example here should be able to listen to the encrypted group call. But like before, in case of chats, here also a compromised or a coerced SP can impersonate one of the users, in this toy example Bob, create a fake key pair and distribute the red key as Bob's public key, thereby creating a PIM channel. So how can this be detected? So currently Teams proposes a security code based solution. The security code is the hash of the public keys of all the participants on the call. So the users on the call are supposed to verify this security code between them, first by computing this security code, and they compute this by getting all the public keys of the other participants from the roster and using their own public key locally to compute the hash, and then they read it out to each other to confirm that they are seeing the correct hash. So in our toy PIM attack here, if they were really doing this, then they would detect it, because Alice, the security code that Alice and Charlie will see, will be different from the one that Bob sees. Zoom proposes a similar solution too for end-to-end encrypted meetings, but notice that this has to be checked. This check has to be done at least once per call, and the security code will change each time a participant joins and leaves the call, requiring the users to participate in this verification ceremony repeatedly. This is also not a very user-friendly solution at all. So this brings us to a new solution space here, which is key transparency. Key transparency introduced the notion of making the service provider's public key directory auditable. And this has several advantages over the manual PIM detection techniques we have been looking at so far. Most notably, it automates the PIM detection, thereby creating a much better and seamless user experience because no manual verification user ceremony is required. On top of that, it provides strong privacy properties, which protects the key owner's behavior, for example, how often they are changing their keys, which groups they might be part of, and so on. So with that in mind, let's take a deeper dive into understanding what exactly is Auditable Public Key Directory on PKD. So to understand this, let us actually look at a classical phone books. So what are the guarantees of a phone book? So if you have a phone book, a physical phone book, everybody can verify that they are seeing their own number, and that is correct. Everybody can expect to see each other's numbers from the phone book. I mean, the way this can be tampered is physically by manipulating the phone book, but this is hard. It has to be done at the time of the creation of the phone book. And also the process of updating the phone book is slow, but that is mostly okay because classically people would not change their numbers very often. Now, if we look at our digital world here with the service provider's key directory, which is sort of a service provider's phone book, which of these things translate? So the first thing is everybody can still verify their own number or public key in this is correct. But the second assumption, which is in the physical world, everybody can expect to see each other's numbers from the same phone book, that doesn't hold anymore because the service provider can be showing different phone books to different participants. Moreover, the slow update process also doesn't hold anymore because public keys can change often when you travel or you switch your devices and so on. So we need a faster update process. And finally, public keys are associated to the user's personal devices. So we need much more privacy, stronger privacy and client-specific views of the phone book for access control. So that's exactly what an auditable PKD builds. The auditable PKD, the service provider, maintains a directory that maps client IDs to their latest public keys. And to mitigate the problem that they can be showing different phone books to different participants, the service provider periodically publicizes a privacy-preserving hash of its directory state to a public bulletin board. The client devices can query for their own and also other clients' public keys, and they'll also get a cryptographic proof from the service provider, which they can verify against the hashes posted on the bulletin board to make sure they're seeing the correct view. So if we look at the landscape of auditable PKD design and development, the first deployment of auditable PKD was done by Keybase in the year 2014, which was great. But one problem of that system was it didn't provide any privacy. So it's a toy example here, but here anybody can see when your devices, which devices got added, when they got added, which is sensitive information because it reveals a lot about the owner's key change behavior. So the Connix was the first system that added privacy to some extent to the auditable PKD system and formalized it. This was published in Usenix in 2015, and Google Key Transparency, the prototype of Google's Key Transparency, used ideas from Connix. And in the year 2019, from this group, we proposed a new system called Seamless, which was co-authored by Melissa Chase and myself. And this was the first lightweight and provably private auditable PKD systems, which improved both scalability and privacy properties of Connix. In particular, we provided a very strong type of privacy, which is no party learns any unnecessary information, which we call zero-knowledge privacy. And we also open sourced the library for the zero-knowledge data structure that we proposed in this work. Since Seamless, a lot has happened in the space of auditable PKD. There have been a lot of recent works, but most of them rely on some heavier weight crypto primitives, such as accumulators, both RSA-based and bilinear, vector commitments, and snarks. And the algebraic assumptions often outweigh the asymptotic improvement of these systems. But on the other end of the spectrum, this is a very exciting time for the auditable PKD technology, where the technology is actually transitioning from academic research to large-scale deployments. So we are already seeing that Zoom has proposed to use a similar style auditable PKD in the phase 3 of their implementation. Novi has open sourced a Rust library implementation of Seamless. So this is truly exciting times for auditable PKD. And it's on the verge of getting deployed by large systems. But that also brings some more challenges with this, which we haven't thought of in the research space. For example, how to build an efficient storage layer for auditable PKD systems, which means not maintaining all the data and the directory and the authentication data in memory, but integrating with the database efficiently. Many of these auditable PKD systems also use an append-only data structures, which keeps growing forever. So how to limit the storage size for large-scale deployments. And then we said latency is very important here. We need fast updates and fast lookups. So how to shard the data efficiently while retaining privacy, integrity, and quick lookups is also somewhat non-trivial of a problem. And finally, what happens in case of catastrophic data loss? Do we lose all the integrity guarantees of the systems, or can we do better? So these are some of the very exciting questions that have come up with the large-scale deployments that we at MSR in this group are actively working on. And so with that, I like to conclude this part of the talk. So I would say the major takeaways here: auditable PKD reduces trust on service providers greatly and provides a fast and automated way for the users to take control in sense of check that the service provider is doing the right thing with their identity keys and distributing it correctly while retaining strong privacy guarantees. And we have seen great progress both in academia and industry in the recent years. We are almost there. We are on the verge of actually seeing large deployments. And from this group, expect to see a large-scale auditable PKD work published very soon. So stay tuned. And with that, I'll end this part of the talk. And I'd like to thank Christian and Craig also for the entire presentation. And to summarize, I would like to give a quick summary, a takeaway from this talk today. So what we saw is our identity and lives are continuing to move online more and more with education, work, healthcare, you name it. And we are also seeing a lot of recent societal and regulatory shifts towards increased privacy, towards giving users more control and trustworthy services. So in the talk today, we saw that research can really give strong guarantees to users that this trust is not misplaced, it is justified. We have in particular looked at two key components here. One is how to minimize information disclosed by users to these services. And the second is how to ensure that the services are correctly operating and managing the user identities and get strong cryptographic assurance to users. So this is a very exciting space and time to be in. So we invite more research, innovation, and deployments here to realize these technologies and empower users to be in control of their identity. Thank you.